Hello, and welcome to today's webinar, Full Field Optical Strain Measurement Systems for Certification of Materials and Structures. I'm Amanda Hosey, your moderator for the 60-minute program, which focuses on hardware-in-the-loop test bench design challenges. Today's speaker is John Tyson II, the founder and president of Trillion Quality Systems. He has more than 35 years of experience in the field of laser-based and optical inspection methods and is a professional engineer with 8 patents gained while developing test applications for the B-2 and Space Shuttle. If you have questions for our speaker, please send them to the Ask a Question box. We'll address as many as possible at the end of the program. Also note that a PDF of today's slides may be downloaded under the Event Resources tab on your screen. Now, on to today's presentation. Welcome, John.
Thank you very much, Amanda. WSU NIAR, the Advanced Virtual Engineering and Testing Facility workshop that we're doing, and we're focusing this presentation specifically on the certification of materials and structures with the optical strain full field measurement capabilities. So what is our Aramis optical strain? It's a non-contact stereo imaging system that NIAR calls the FEA of testing. And the reason why it's considered the FEA of testing is it's based all its strain measurements on 3D shapes to begin with, which allows us to do 6 degrees of freedom tracking of components, and allows us then to do 3-dimensional deformations and the full strain tensor across the whole field of view of a measurement, as if you had 10,000 rosette strain gauges across the field of view, as well as every other calculation that you can do with 3D coordinates and time. It's also a certifiable strain measurement, which we'll be talking about today, compared to a strain gauge where it's really based on the operator's capabilities and design of the test. The actual certification is solely of the amplifier itself. With Aramis, we can actually put a gauge block in the field of view and measure the strain accuracy of the system for every test. So it's a certifiable strain sensor, and we utilize our 3D sensor as a certified sensor. We factory certify it to traditional standards, the VDI, VDE standards for every system that we produce. We use certified calibration standards that are certified to third-party measurements and have a certificate for each one. The operator can then set the fields of view desired and lock them in, and then allows it to stay stable for long durations, long-term testing, and this kind of thing. Because it's all fixed-based, the system is very easy to use, really lowering the operator requirements and making it as simple to operate. We can also implement with templates for guided operation of the system, so the operator needs even less training. We also have what we call total recal for instant recalibration of systems during structural testing. So we can be monitoring for days, weeks, years at a time. And it also is coupled with automated reporting, which allows all the tests to be reported exactly the same way. So you have comparable results throughout all your measurements. The Aramis optical strain is really an industry standard measurement. It's approved by most major organizations that we work with in the aerospace, automotive, biomechanics, and microelectronics industries. We also have the IDEX Society, which is our International DIC Society. This is governed by NIST and Sandia and is setting the industry standards and certifying inspectors. The equipment is also used by tens of thousands of companies all around the world. So the IDEX conference is again the International Digital Image Correlation Society, and it's really setting the standards for the inspectors. One of its first and really great guides that they've generated is the Good Practices Guide, and this is downloadable from their site and or from the main site, whichever makes sense. And it also offers high-level inspector-level training and certification. We're currently offering level 1 certifications, but level 2 and level 3 are being worked on and developed. So Aramis optical strain is designed to work like a lot of your standard mechanical sensors, but mechanical sensors are just single point sensors, which typically take a lot of time and effort to get implemented. And you're sitting there trying to make measurements and on these complex results that we now see in finite element modeling. Aramis is really a full field capability, so it allows you to directly interface with finite element models with full field data. So it allows you to really understand the what the reality is that finite element modeling are trying to model. That's why NIAR calls it the FEA of testing. It's also extremely accurate, considered a Class A extensometer, the highest accuracy available. So the system is a stereo imaging system. Just like our two eyes can measure where something is in three-dimensional space, the cameras now do it quantitatively and precisely. So we can use a target dot in the field of view. We have many target dots in this field of view as our measurement points. We can also use it as reference. So we are using, in this specific case, the knee as reference for these measurements of this prosthetic. So the data is accurate in three-dimensional space, down to the micron level. Even though everything's moving in the field of view, we're referenced to the knee, and so the coordinate system is moving with the part itself. Incredibly powerful. And then the setup time is just a fraction of the time as mechanical sensors. This test probably took 20 minutes to get set up. We can also put a pattern down, and the pattern allows the software to create targets, continuous targets across the pattern. And this allows us then to see holistically what's going on to the structure. A clip gauge or a strain gauge is going to give you some average value that you see here as tremendous local resolution, to the extent that these Lüders bands up here are crystalline level response of this steel going through test. And so we're seeing right down to the crystalline level response of the material, far better than any strain gauge, clip gauge, or model can really calculate or measure. So the system is very powerful in the sense that not only we're measuring full field, we can bring the CAD model in, so all the data is going to be in your true CAD coordinates. We can get the results and see full field the results that are happening. You can put your gauges down after you already know the results, and so you can really interrogate the results and get the data that you want for your measurements. It's a non-contact measurement, so it's fast and efficient to set up and measure. It's full field, so the idea that, with a strain gauge, you need to estimate where the strains are going to happen and then put the strain gauge down. Here with full field, not only do you get the absolute strain in the right coordinates, but you also can see things that you may not have expected. We call it the engineer's toolbox because not only are you measuring strain, but you can say, well, what's the displacements that are causing these strains? What's the CAD underneath the structure that's causing the displacements that are causing the strains? You can really interrogate the results. The system is an optical system, so it can do multi-scales, go from very microscopic fields of view to very large fields of view. We have, individual solder balls that we do strain measurements on to entire wind turbines in operation measuring. Material independence is a critical capability. The idea that a model can model a material very well, but modeling a system is much more complex because there's a lot of assumptions that go on between the different material interfaces. a strain gauge, you put a strain gauge on a material. But with Aramis, we're measuring the full structural response. So we can see how metals and ceramics and elastomers all work together. The complexity of composites and understanding how it's really working in three-dimensional space. Our equipment, we can just use a broad range of different cameras. Most cameras can do quasi-static to low dynamic without any issue. But we also have cameras that can go up to 5 million frames per second, which we use for glass fracture and these kinds of things, but are just complete range of capability of high speed. And we'll be talking tomorrow about high speed work. When it comes to vibrational measurements and other kinds of high speed values, compared to like an accelerometer, we're measuring the true operational deflection shapes of the material. Compared to accelerometer, we have to interpolate to get those operational deflection shapes. And the fact that we're measuring it directly gives you just much greater capabilities. So we're bringing reality to your finite element models with true physics-based modeling data. NIAR calls this physics-based modeling the concept that you understand your materials well, you understand your component and processes well, then your component testing really is making sense. And by the time you get to your structural testing, you're structurally testing the full system, not just that test. When you get into material testing, we like the finite element model. It looks beautiful. And we say, well, you know, the Aramis really should be a little bit better to match the model. Actually, it's the other way around. These local variations are the true variations in the material. And the Boeing modelers say, we need your experimental data to really get our models to match reality. When you get into real structural testing, normally you put a strain gauge down based on what the model says, but many times the model is very different than what's reality. In this specific case, there was a core splice in this blade that was not in the model, and so the strain fields are completely different, and the results are completely different. Only a full field data can give you these results. So people wonder, you know, how difficult is this to use? Using our Aramis operational checklist, and it's somebody who's been trained on the equipment, this chart answers all questions that you want to make. If you want to match a 3 millimeter strain gauge, which would be typical, a 12 megapixel sensor, you can use a 400 millimeter field of view with this pattern size and this target size, and always get great results. So just follow this chart, and really, that's all you need to know. The fixed base sensors stay calibrated for long periods of time. You bring your finite element model in, and now you're oriented precisely to your coordinate system. When you get into material testing, as we saw before, the Aramis provides, you know, much finer data than you can with a strain gauge or a clip gauge. And the complexity of materials today just makes it much more complex, especially when you get into composites. And we were talking earlier about chopped fiber composites that, you know, it's just full field methods is the only way to understand. But NASA Glenn, going originally with epoxies, but then onto their composites and then onto metals and other things, have described, even for metals, they're getting much more consistent material properties with a full field method of Aramis than utilizing traditional methods. And our software is set up to automatically calculate all your primary parameters. And you can set this up as desired to always report automatically, to the point where Boeing uses our equipment with a robot, and robot just does all the testing completely automatedly. So let's talk a little bit about certification history. And so I'll be talking about each of these. And each of these applications it has certification papers that have been written and are documented. And we have a NASA Tech Briefs article that is coming out. This optical strain measurements and certification is the basis of this presentation. And the papers I'll be presenting here are all captured in this presentation, this paper. Early on, we were working with NASA Glenn and NASA Johnson on the return to flight of the space shuttle. This work down at Southwest Research was utilizing high-speed cameras off of a mirror at the inspection area. And we use mirrors all the time. But at the time, NASA and Boeing were very critical of our measurements. And we went through a month-long certification process. This is written in a paper that was done by NASA Glenn, NASA Langley, and Trillium Quality Systems on this certification process. This data right here was the data that NASA used to validate the LS Dyna models to get the space shuttle flying again in 2005. So this was just the critical data necessary to get the space shuttle flying again. About the same time, Lawrence Livermore National Labs wrote a validation paper on Aramis and showed that Aramis was comparable to traditional gauges. They then went on and wrote another paper that took single crystal loadings and measured the stress-strain curve on all 9 crystalline axes simultaneously. They said it's not possible any other way. And this incredible work was done in 2006. Just to give you a sense of how long this technology has been around for and validated for. Another interesting application where done at Wright-Patterson Air Force Base, we validated Aramis thermography to be able to measure not only the full field deformations and strains, but the temperature map also combined with it, so we can use the temperature change to correct the thermal expansion in the mechanical strain measurements to get the true mechanical strains in the measurements. This went on to be applied at Edwards Air Force Base on the B-2 bomber. And you can see we've patterned the aft deck of the B-2 bomber here, and we're getting the full field strain measurements and temperature response. This was all reported at the Aircraft Structural Integrity Conference in 2008. We now use Aramis thermography throughout industry as just a very powerful tool of adding not only shape, deformation, and strain, but temperature for every point in the field of view. All the rest of the results of this report were highly secret, but at least we got some data out of it. The interesting thing is that NIAR, which we are here today at NIAR, was the first customer for Aramis in the United States. And we were working on trying to solve a shear panel, the shear panel measurement with laser holography back in the 90s, and came across this digital image correlation technology and brought it to the U.S. to be able to specifically solve this problem, and the rest is history. So in shear testing, typically you understand where this plate and this plate are moving to, but you don't really, you're making assumptions about what the shear result really looks like. In this data with a full field method, you're getting the full, with hundreds of gauges, the strain map in the shear section, and actually seeing shear banding, which is, theoretical, but here you're visually imaging it. Just incredibly powerful, not only for understanding your materials, but how about for teaching mechanical engineering? Boeing wrote a wonderful paper in 2012, really looking at their comparison to strain gauges. Basically, every material testing machine at Boeing has an Aramis system on it to get that full field material properties. But they went on to talk about failure modes in composites and the idea that Aramis is giving you this full field result. It's calculating the strains right during the failure modes, and it allows them to be able to directly compare the failure modes with the models. And they say here specifically, this cannot be replicated with strain gauges. When they went into other complex composites, the the complexity of this data, no matter where you put your strain gauge, you're going to be getting different results. But here they're able to truly understand exactly what's happening into their structures and compare it against their models. They went in to talk about extreme environments, and we've done work with them at high temperatures, in vacuum, in the creation of composites in a vacuum thermal chamber, and in this case, working at materials that are beyond the limits of existing strain gauges. Or going to very high deformations and strains. In these structures, 100,000 microstrain and a substantial amount of displacement. And in this specific case, we are doing 1 million microstrain. And in this specific case, strain gauges failed long before the end of the test. So we're applying these technologies to a broad range of matrices, measurement matrices. And the idea that we could, if you want to look at complex strain fields, the cost of strain gauges would be prohibitive. Even extensometers are just hard to understand the local resolutions that are happening. And especially when you get into compression testing or very large deformations. And so these are just some of the examples of how this works. And so in the end, it's just way less expensive to use Aramis for measuring these same traditional measurements that you normally make. When you get into complex data sets, the idea that, of course, we can measure where you want to put the strain gauge, but you get the full data set all the way around that area also to truly understand what is going on with your structure and your materials. When you get into balancing, obviously something that needs to be done on a continuous basis, you get data across the whole field of view, so you can directly choose the balance points that you want to monitor and then be able to measure, making sure that you're balanced in a correct way. So basically, Aramis being used extensively at Boeing, from very large to very small fields of view, high temperatures and vacuum conditions. Obviously, space is a big area for us. We're doing testing of materials right before failure and understanding the failure modes as they move across the field of view. And it becomes this low-cost method for measuring the data that is critical in today's world. A VP of Boeing had said, strain gauges are costing us too much. Find a better way. The report back to them by Boeing Engineering was that Aramis was 10 times cheaper than strain gauges, 50 times manpower savings or schedule savings, and 100 times data improvement. We were then used on the FAA 787 certifications, which was quite powerful. So here's just an example of 2 strain gauges being used and trying to understand the response of this structure. So here is the location of the 2 strain gauges and the response over time. But we can understand much more deeply the actual strain field, the vector of strain throughout the field of view, and truly understanding how this wing pylon is responding to the applied loads. Again, on the structural testing of the 787, they had over 10,000 strain gauges, and we added 4 Aramis systems in and around the wing root, which had failed in an earlier test, adding another 200,000 strain gauges. This was critical to the FAA certification because it proved to the FAA there was not another load path they didn't know about. And so this led to the certification of the 787. Now, in structural testing, we're trying to reduce the cost of structural testing by 50% and reducing the labor as well as faster installs and saving on schedule. But the benefit is that they get more and better data, all synchronous. And we have applications where on NASA Marshall, we have 25 systems studying a launch vehicle. So all the instrumentation is the Aramis equipment monitoring the displacements that are happening Another good example was this composite spars at General Atomics. In this case, for the Air Force, we tested 60 spars. They had put 15, 16 strain gauges on each spar. We asked at the time, why are you putting strain gauges on when you have an Aramis system and we can just be measuring it with Aramis? The program manager didn't know that about Aramis and said, well, let me call the Air Force and say, is it all right we use it? And the Air Force said, absolutely, Aramis is fully approved. Cost of Aramis, $0, because they had the equipment. The cost of the strain gauges was $1.15 million. So you think of the strain gauge being not so much, but in the end, the strain gauges cost a tremendous amount. Correlation, within 0.5%. And so the difference, we believe, is because just a slight difference in measurement location, but beautiful correlation with the strain gauges. So model validation with a test. Of course, we're here at NIAR, which is the Advanced Virtual Engineering and Testing Facility. And so this is the reason why they call Aramis the FEA of testing, because they can go in and compare directly with a finite element model the true mechanical response, what Aramis does. When you get into real measurements, this is just a very simple example where you have a wrench trying to work, looking at the strain fields on a wrench associated with loading up, torquing a nut. Interestingly, the comparison to the FEA was showing a huge difference here in what the model was showing compared to the simulation. Such a simple thing. How could it be any different? Turns out that the mouth opening didn't match the bolt that was being used that accurately. Just a simple thing, as the bolt was not modeled correctly in the part. When we changed the simulation to match the bolt result, then the model then is matching very much more closely to the measurement that we did. So here's a perfect example of, iterating the model to match reality. We also did a chapter in the AS&T handbook on non-destructive testing overview, a section called Optical Measurement and Strain Displacement. We did this in 2012. It's continued work there. Typical example here being the skin being pulled off of a composite where the strain is moving across the field of view. Here we're monitoring the forces, the crack length, and the strains and displacements all simultaneously. Really a holistic value of data. On the James Webb Space Telescope, which of course we're very proud of have been a part of, they wrote a complete article on the certification for our measurements there. We brought in 4 Aramis systems for looking at the 4 sides of the satellite itself, the bus structure they call it. And we just replaced 87 LVDTs, but they actually we put on more target dots, which became critical to the measurements, and we saved them $2 million in that 3-month test. And that equipment was in 2014. They have that being used every day for free. Another fabulous paper here done by Dr. Paul Gradle on using DIC on large rocket scale testing. He talks a little bit about very high speed, 70,000 frames per second measurements, a very high temperature here at 1700 degrees F, vibrational dynamics where strain gauge couldn't even survive, full field structures, an 18-foot tank where we're getting full field strain data on that, complex compression results, and we were doing work. We got the the final launches of the space shuttle, they had a problem which would have canceled the last 3 flights, and we solved that right on the launch pad on the external fuel tank for the space shuttle. It was just incredible work we're doing. In this case, we can see, again, we were talking 70,000 frames per second, being able to capture the explosive strains and displacements of this component. Just no other way to do it. How about hot-fired rocket motors? You know, be able to measure, you can see the Aramis system in the background, measuring this rocket motor being fired. This was work that Dr. Paul Gradle had done early on to validate the technology and develop patterning methods and that kind of thing that would work well for them. They validated the equipment to making measurements, and they always had a difficult time having strain gauges survive the testing. But then there would always be these arguments about what the measurements mean. He said, after we did full field optical, he said, now it's intuitively obvious what's going on, and there's no more arguments. Then he took it on to the J2X ultra-large rocket motor testing at Stennis, NASA Stennis, and making measurements on components in the engine. You can see our Aramis system up here looking down at these components and making measurements during the whole engine run so they can truly understand what's going on the components during, you know, these cryogenic fuels operating at very high temperatures. I mean, just an amazing world to be in. And here we're making precision measurements throughout the test. So, of course, NASA Marshall, we're dealing with dynamic measurements. They're expanding the capabilities of the use of the equipment and sharing all this data with industry and government. This is a good example of a paper that he wrote about that. This work on the Vulcan spacecraft, we're just using simple patterning, using a vinyl sheet to pattern the rocket motor. In this case, this is the SpaceX Merlin engine, and I patterned it with vinyl myself in 2 hours. It's 8 feet in diameter, 10 feet tall, and just very fast and efficient, getting full field data. Imagine one man strain gauging this. On the Vulcan launch vehicle, they did a compressive loading on this, and these are where the strain gauges were, and it failed over here, so the strain gauge data was meaningless. So here's just an example of a large structural test on an aircraft. We see, as you can see by the histogram here, most of the data happening 20 millimeters of deformation into the test, looking at the total deformation. But if we look at the motion correction, so we're now expanding just this region of where the data is in the field of view, we can see the local variations that are happening well within a fraction of a millimeter. When you get into the principal strains are going to be varying as you're cyclically loading the material. You can see the data moving around. Here we can just show where maximum strain is, wherever it is on the part, and it localizes as we go into max strain positions. And then when we get into the epsilon y, you know, now it'd be a vector of strain that you're interested in here, and you're understanding exactly the strain fields associated with that vector of strain. And you can choose that orientation here. Here's the y vector in this case. So we're measuring the strain in this vector for the material. When you get into string pots used extensively in the aerospace industry and automotive industries, the string pot takes a reasonable time to get set up. I mean, literally days, where this patterning, putting target dots up on this wing, just took 60 minutes, including the whole test. And the modelers that we were working with said that the linear data from the string pots is pretty meaningless to them. But the 3D measurement that we're collecting is much more useful in direct model comparisons. Here's an example of a test that we were running. You're seeing the twist in the wing from the front to back. So there's line of sight measurement, no interferences like a wiffle tree touching a string pot line. You can choose the vertical, you can choose your reference in the field of view even after the fact. You can use the vertical stabilizer or some structure in the field of view as your reference for the measurements. In this case, we're using the floor, the structural floor of the building to do the measurement. And so you're saving on schedule, getting real-time accurate data, and really with no operational costs. You know, it's just a capital equipment purchase, and then there's no operational costs beyond. On structural monitoring of landing gear, Boeing has decided that all landing gear tests now are tested with Aramis. On the 777X, they had 8 systems and 120 measurement locations they wanted to do, and they did 15 cycles of the landing gear, which took about a month. We recommended that we implement a robot into doing it. With 1 or 2 systems, you can do the entire landing gear testing in 1 cycle, which would have taken a week. And so it would have just tremendously saved on the measurement time and effort. And we couldn't get it implemented in time, but the methods are easy there, and robots are cheap nowadays, so it works well. At CRADA, that we did with Wright-Patterson Air Force Base, was using our Aramis system to track in 6 degrees of freedom, in this case an ultrasound probe, and be able to automatically map the ultrasound onto the structure, just saving a tremendous amount of time, giving real-time mapping to the CAD or to the surface of the material, giving true documentation of your hand-scanned NDT, and mapping it all into the XI digital twin. Typical example of the same thing. In this case, we use a thermal sensor, and we just ran the thermal sensor with a heat source across the material. Here you're seeing the bond line thicknesses, you know, the internal structure, typically with thin-skin materials. And this works nicely. We're coupled with an ultrasound producer, where the ultrasound robot can scan a part and look at the internal structure, and the thermography can look at the surface and understand the surface results that the ultrasound can't really see. Getting into digital manufacturing, again, we're going to use the Aramis sensor to, in this case, with a touch probe, it's a CMM machine. You can go around and make critical measurements as quickly as moving your probe to where you want to go. When you get into manufacturing, you can position components extremely accurately right to CAD coordinates, but you're going to be tracking the real component into the real position. And even compared to hard tooling, this can give you a better product in the end. And we can then capture each assembly, and the quality inspection of the position of the component comes out as free with the measurement. It also becomes very powerful when you use things like click bonds and for positioning. We're typically 10 to 50 times faster than doing it mechanically. Or we can just take any tool that you have, in this case, a wing alignment tool or flap alignment tool, and just digitally capturing the 6 degrees of freedom of the alignments. So in this specific case, we're watching the operator position a click bond, and the RVAT software gives the operator instructions. He doesn't even need to know how Aramis works. He's just given instructions on how to do it. He can add comments back again. So we've built this little tool, and this tool then clips onto the click bond, and the software then tracks it. So we just go into tool tracking, and it is now tracking the click bond and showing the operator where the part is on the surface. And so he can check whatever tolerances you have. You can track to the tolerances that you've set in the system. Then the operator clicks the click bond, mounts that one. he can then just go up and pick up the next click bond and go on and track the next one. At Northrop Grumman, we were doing some work at Vandenberg Air Force Base. It takes them a day and a half to put 10 of these click bonds down. And here we're tracking, as you can see, in real time. We can put 10 click bonds on in 10 minutes. And so you get a sense of precisely where the click bond is going and be able to track it with high precision in 6 degrees of freedom space and document each of these steps as they've gone through. So at the end of each one of these positions, data is outputted to the XI Digital Twin, and we're capturing the location of each of these click bonds. Another powerful feature is to be able to do the same thing with a drill adapter. In this case, again, being able to drill a component on complex composites where you can just put in the drill guide requirement that you have, the bushing, and now we can be tracking this. Again, gives you complete guidance on how to do it, and tracking with 6 degrees of freedom where this component is in place. Once he's positioned it correctly, he can either hold it down, hot glue it in place, whichever works the best, grab his drill and drill it. And he can be drilling into a hole below that he can't even see. Blind hole drilling, it works very nicely. So here's just an example where at General Atomics, they were more than 10 times more efficient at doing the drilling operations on wings and things like that. And the QA just comes along as part of the measurement. And again, talking about blind hole drilling, you can drill literally into a hole below, even if you have a skin on top, because you can track exactly where that component is. When you get into 6 degrees of freedom, an adjustment of a hard detail like this with this has 6 axes of freedom, and you compare this to a tooling setup like this, where each one of these takes 3 to 5 hours with a laser tracker to track in. We're working with Lockheed on this and developing for their adjustable details the ability to, with our virtual inspection, guide the assembly of the fixture and then be able to position each one of these into position. So a typical example here is, again, with the RVAT instructions. We're seeing the operator, instead of 3 to 5 hours to adjust this detail, he's going to do this in 3 minutes. And so basically, he just turns on the tracking. It gives him the ability to show the X, Y, and Z location as well as 2 angles. You can see he's getting the 1 angle in position correctly. And then he's just going to go in, excuse me, and adjust each of the other parameters. This entire alignment, just takes 3 minutes to do. And so he's guiding this in true 6 degrees of freedom instead of the iterative effect of being able to position, position in X, Y, and Z and then check all the coordinates. So I let him go through all the positioning here, but literally 3 minutes with a laser tracker. This is 3 to 5 hours worth of work. And he's done. So when in digital fabrication, we're doing a lot of work where we're doing pre-fit shim and trim calculations on things. We can put it together, the scan of each part, and then put them together, make sure there's a shim or a trim required. Then during manufacturing, literally the measurement of the structure and the component being put in, we can measure the bond line thickness. This is done on every structure at General Atomics, where they measure the bond line thickness, validate that the part is meeting the requirements. A too thin bond will not hold, a too thick bond will not hold. So making sure your bond is correct. But then you have things like this where the bond line thickness was wrong, and we can say right back to engineering where the problems exist, documenting each step as we've gone along. And captured in the XI digital twin, each component during the assembly, automatic checks, and then the quality manager can then sign off on each one of these, and each component tracked with QR codes. Here's just an example of a virtual assembly. We're tracking these holes in the back of the device, which the operator can't see, but he's given color guidance on where the component should be, and then given precision accuracy measurements of where those holes are in the structure. And so he can be tracking things that he can't even see virtually. In production applications, we can take our SUPAR, which is our augmented reality tool, where we can literally take a vehicle like this and show where various brackets need to be mounted on the assembly of the car. So we have all kinds of applications that we work with in augmented reality, from tooling inspections, where we have an incoming inspection, making sure that tooling is built right, has all the holes, all the welding is correct. We get supplier checks to make sure the parts are coming in correctly, tooling alignments and assemblies, making sure that every one of these components is positioned correctly. I mean, how do you validate this any other way? It must take hours and hours and hours. Here you just walk up to it and you see the CAD overlay right onto the visual object. When you could do in the case in the automotive world called body in white, where they have to check all these holes and all the welded studs on this part to make sure they're all in the right location. We have just quick assembly and measurements we can do. When you do assembly instructions, welding instructions, logistic rack inspections. Of course, with logistic racks, you're always using the cheapest supplier, but you really should inspect how they are, or your parts are going to be damaged in the process. Going to final inspection of your vehicles, etc. Here's just an example of real-time interactive display of an operator for an operator. In this case, we have a tool. We're locking the CAD onto the tool with our augmented reality, locked on. Now we can overlay the CAD with the live image. And so this just becomes so powerful to just rapidly be able to see if there's anything wrong with the build. You can put in the component that's going to be sitting on this tool. So this is a virtual tool, and you can actually see exactly where the parts are going to be sitting in, rapidly report any problems that are happening. This implement part of our inspection program. We can also take our Aramis and ATOS results, overlay them in the AR, walk up to the part, mark any problems that are happening, and ship it off to your production manager so he knows what's going on. In this case, we took our CT and we're overlaying the CT right onto the part sitting, as you can see, on a stool. But you can see the CT data. Zoom in on it, and you can actually document where the problems are, if there are any, and what the dimensions are from the CT measurements that we did. And so it just becomes this integrated tool as part of our optical metrology capabilities. So Aramis optical strain is, again, called the FEA of testing for good reason. But all our optical metrology tools are really just tied together. We have our Aramis optical strain. We have high-speed data that we work with. We have a whole webinar about that tomorrow. The Aramis thermography adds this whole other layer of thermal mapping to the deformations and strains that we're measuring with Aramis, and allow us to correct the strains for thermal expansion to get the true mechanical strains in high temperature environments like the B-2 bomber. Our ATOS scanning gives precision scanning. It's the premier scanner in the world for understanding how the Aramis works, all these tools working together. The Zeiss CT uses the GOM software also for 3D X-ray and understanding the metrology of how all these parts are working. RVAT sits again on top of Aramis and allows you to do production photogrammetry in a completely guided process. And then the SUPAR gives us this interactive inspection capability that, again, ties all the pieces together. And the XI Digital Twin, based in 3D coordinates, is coupled with all these technologies, as well as any other measurements that you do to bring your production line fully together. Thank you all very much. And this has been a presentation from Trillion Quality Systems. We're a GOM certified partner, which is now part of the Zeiss team. We're now part of the Zeiss program, and very proud of that. We have offices around the country, Seattle, Philadelphia, Detroit, California, Huntsville, Florida, and soon in Wichita, providing systems and engineering services to support the implementation of this technology for more than almost 25 years. Any questions?
Thank you for that presentation, John. Just a reminder to the audience, you can still send in questions for John through the Ask a Question box on your screen. Now we're going to take some questions that have already come in. First up, John, how difficult is Aramis optical strain to use?
So Aramis is a tool like any other tool. We have training programs that happen quarterly in each of our offices, as well as at customer sites. And we have level 1, level 2, level 3 certifications for these operators. But the equipment is designed to be easy to use, implement, and used in test as well as manufacturing and in structural health monitoring for long-term monitoring of structures. And so the technique of patterning something is very straightforward, but it's the artistic part of preparing the Aramis equipment or using target dots or sheets of material, that kind of thing. And then the actual measurements follow a simple guide to the operation of the equipment. Obviously making good measurements requires training, and we look forward to supporting customers throughout the life of the equipment that they have.
Great, thank you for that. Next up, why is optical strain more certifiable than traditional strain gauges?
Traditional strain gauges are very much operator dependent. An FAA DER is going to be certifying that the amplifier has been calibrated within the last year. But the actual strain measurement is totally based on the correct strain gauge being applied, it being applied in the right position, and applied correctly. That obviously requires a tremendous amount of training and experience to do that correctly. Where Aramis, we can put a measurement block in the field of view with the same size pattern that you're using and validate that everything was set up correctly and that what the accuracy of the measurement actually is during the measurement that they're doing. So it's you can validate every measurement that you do right down to every facet of it.
Great, thank you. Next up, are there any use cases in fracture mechanics or slow crack growth?
Yes. So one of the beauties of Aramis, one of the reasons why Boeing implemented Aramis originally was because of fracture mechanics in large grain titanium structures on the F-22. And we were doing work where we're monitoring the crack growth and the crack strength of this fracture tough material, and watching the strain crack propagate across and go around big crystals in the titanium. This just was not possible with any other method. We did some other wonderful work at the Navy where they had taken parts, aluminum structures off of shipboard, and we were able to measure the mode 1, mode 2, mode 3 response of the fracture as it was crossing the panel. And there's just no other way of doing these measurements. And so we can track the crack tip as well as all the parameters of a fracture.
Great, thank you so much. Well, with that, we have reached the end of our webinar. I would like to thank John Tyson II, as well as our audience, for joining us, and thank you to everyone who submitted questions. We'll supply John with any that we didn't get to so that he may reply by email. As a reminder, you may download a PDF of today's slides under the Event Resources tab on your screen. In just a moment, a survey will pop up. Please tell us what you thought of our program by answering these 3 questions. This webinar will be available on demand for the next year, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, thank you for watching.
Thank you very much.